All right, good afternoon, everyone. Let's start. So first of all, you might have seen that we have released homework 5, our last assignment in this semester. And only one assignment. And there's no other assignments anymore. And what you need to do is that to finish this last assignment in time and wrap up your project report. We have released the due for both the project report and the homework 5. And again, the workload for homework 5 is quite light, only 3 problems. Unfortunately, they're all practical problems because in the last few sections, last section we discussed was all about the practical applications and how we apply learning methods, inference methods to specific models. So we do hope you can implement and test those algorithms in practical data. The data is really small, and you just follow what we have discussed in class. We have all the mathematical details, we have algorithm steps. Please implement accordingly. However, again, don't try to finish it at the due date. Like in you only have like 24 hours left or 48 hours left. You might not have sufficient time to debug your code because it's not like writing something, right? Where you need to do just calculate and write down some derivation. This is some kind of programming. You do need to allocate some time to debug your code. And I'm pretty much sure most of you knows the basic ideas and all the algorithm steps, but when you convert it into executable code, there might be some problem. That might be some weird problem. So please start doing it right now. And please try to leverage the office hours. Right? And ask me or ask our TMs to help you as much as possible. Don't wait until the last day and say, okay, I don't have enough time to do that. I have a lot of other dues. I have final exams. Can you please extend? Yeah, we try our best to extend if it is possible. But for the final project report and final assignment, we do have some strict deadline from campus. Like we need to release the grade in at a certain period. So that will be much less flexible than other assignments. So again, please start doing right now. Okay, any question regarding this last portion of the final exam, not final exam, the assignments and the project report? Everyone is fine with that? Okay, great. So let us continue with the Bayesian neural networks. So in the last lecture, we have introduced the most commonly used approach to train neural networks, which is called stochastic Bayesian optimization, stochastic optimization, right? And then we discussed the probabilistic or Bayesian formulation of neural networks, which actually is quite straightforward, right? So we know that generally for a neural network, we can view it as a series of linear and nonlinear transformations, right? So suppose this is the input layer, which consists of the original input features or feature vector. And then to get the neurons in the second layer, we usually first do a linear transformation. That means we're going to multiply a weight matrix with this input layer, and then perform a nonlinear activation function per element or element-wise. Then we get the output of the second layer, which are denoted by x and 1. Right? And similarly, we perform another linear transformation and a nonlinear activation function to get the neurons in layer 2, right? So we get layer 2 equals to, first we multiply a transformation matrix with the output of the layer 1, right? And then you perform some nonlinear activation function element wisely to get the neurons in layer 2. Just keep doing that until you reach the last layer, right? And the last layer, according to the tradition of this community, we just do a linear transformation, meaning that we multiply WL with the output from the second last layer, and then we get the final output or final prediction. We don't do nonlinear activation anymore. And we emphasize that this is actually not necessary. If we want to do that, we do that. But in the history of neural network, people are doing things like this. Okay. And as we discussed before, right, the actual parameters of neural networks are those transformation matrices on each layer, right, between each layer, W1, W2 to WL. And if we want to formulate the neural network as a Bayesian model, it's very natural. We just assign some prior distribution over those transformation matrices or weights. Right? And you can imagine in that way, we will those W1, W2 to WL as random variables. And because the neural network output essentially is a function of the input and also those transformation matrices, because those transformation matrices are random variables, the output must be random variables. So this is a whole probabilistic framework, right? So if we write down the joint probability, it has a very simple structure. We got a joint probability over the weights of the neural network across those edges, right? And then the data, right? So we got prior of the weights, and then we use those weights to generate the outputs of neural network, and using the output neural network to sample the observed outputs, right? And that's the basic framework for Bayesian neural networks that basically applies to arbitrary type of neural network, right? And then we'll talk about the commonly used likelihood, right? If your observation, your observed output is continuous, then they often use likelihood as just a Gaussian likelihood. You assume your prediction is the correct one, and then through some white noise corruption, you observe, you get the observations. That's why you apply a Gaussian likelihood. If your output, your observed output is a label, a binary label, like whether the stock price will goes up or goes down, right? Or whether the tomorrow is going to rain or not, or it's a binary classification problem, then in most cases we're going to use Bernoulli likelihood, right? And then the neural network output essentially models the probability the label is 1, right? So they parameterize the Bernoulli likelihood, and of course, to ensure that your output will give, the neural network prediction will give a valid probability, people often place a sigmoid function over the output to convert it to a valid probability, which is must be between 0 and 1. And if you're doing categorical distribution, which is very, very common in image related problems, like you want to classify the objects in the images, you might have 1,000 categories or 10,000 categories, right? And then you're doing a multi-class classification, then in most cases, we're gonna use a categorical distribution and the so-called softmax, namely your output will be a vector. So suppose you have k categories, the output will have k scores. Then you just take the exponential and normalize it to get the probability. You classify each, you classify this example into a particular label, right? This is what we have discussed in the last lecture. So once we have specified the joint probability of our Bayesian neural network and model and data, our goal is to estimate the posterior distribution of the neural network weights given the data. And then once you have this posterior distribution, we can follow the formula we have discussed before. We can use this integration to calculate the predictive distribution, as we mentioned before. This is the benefit of Bayesian framework, because the predictive distribution is gonna integrate out all possible predictions according to the posterior distribution. So it tends to be more robust and more accurate. So those are basic formulation of Bayesian neural networks, and just help us to refresh our mind and record the definition, right? And then we talk about how to do this inference. We have specified this Bayesian model, right? And our goal, we have just mentioned, want to compute the predictive, the posterior distribution of the neural network weights given the data. And of course, this is very hard. We can apply Hamiltonian multi-level sampling, as we mentioned before, which is nice. However, it is often too slow to be practical. So instead, right, we're going to use a variational inference to sacrifice some accuracy, but at the same time to make the problem much easier and much more efficient to address. So there are a variety of methods doing posterior inference for Bayesian neural networks, but here we're going to introduce a very classical and popular one, which is called Bayes by backpropagation. Of course, this is a instance of the variational inference framework, right? So we know that to conduct variational inference, we need to first design an approximate form of the posterior distribution, right? So let's just emphasize again the idea of the variational inference, right? The variational inference, the idea is that, okay, suppose this is a true posterior distribution. Right? So we know that by using Bayes' rule to compute, this guy is infeasible in most of cases, right? So how can we sidestep this issue or alleviate the issue? We're gonna specify an approximate form for this guy. Right? We denote it by Q of W. Q of W is just our approximation to the true posterior. However, to make the computation feasible and efficient, we're going to restrict the form of Q of W to be very simple, like just the diagonal Gaussian, right? And now our goal becomes, okay, from this approximation family, we want to find a special instance which is closest to the true posterior. That's the idea of variational inference, right? So in Bayesian neural network, what is the commonly used approximate form for the posterior distribution? It is a fully factorized Gaussian. So basically, we assume the posterior, or we design an approximate form of the posterior as a factorized Gaussian distribution, which is factorized over each individual weight in the neural network, right? And for each Q of Wi, we assume its form is a single Gaussian, right? So it is parameterized by the mean and the variance, right? So here this is a bit similar to mean field, but it's even more restricted than mean field. Right? Mean field, we just assume, okay, your posterior is fully factorized over each individual elements, right? But usually we don't specify the specific form of Q of W. But right now, you see that even if you want to use mean field, if you apply a mean field formula, you still don't know what is the exact form, optimal form of each Q of W. So to further make a restriction that I'm going to assume Q of W is a Gaussian distribution. That will make a lot easier. But of course, if you want to use other distribution, you can use that for sure. Like you can use student T distribution. Right? But here, let us just use the Gaussian distribution. And here, when we parameterize this approximation form, the mean is okay. It's just use a free parameter mu of I. But the variance, you need to guarantee the variance is always positive, right? And one way is that, okay, I'm gonna just represent this variance by V of I, but then when we do the variational inference, we're gonna add extra constraint that Vi is non-negative. But doing this is not very convenient because you have to do some constraint optimization. It's not very, it's very inconvenient, especially if you want to use stochastic optimization. So another commonly used approach is that if I want to incorporate positivity constraint, we can just re-parameterize my variance in this form. So we can assume the variance is actually calculated by logarithm plus 1 plus some exponential of a free parameters rho of I. In this case, you don't need to put any constraint of rho of I. No matter what value rho I is, this log 1 plus exp is always positive. Okay. In this way, you can optimize mu of I and rho of I, without any constraint. That's the benefit. And someone asked, why should we use this form? Why not just use exponential? Yes, you can use. You can even use rho I squared. Right? But this is just the form chosen by this back propagation algorithm. You're free to choose whichever form you like. And then once we have given the approximate form of the posterior, namely we specify this family, right? And then we can construct a variational model evidence lower bound, follow the standard framework, which essentially is to derive this integral, right? This expectation of this log fraction. The fraction is between the joint probability and approximate posterior. If you do some kind of simplification, you see that it can be decomposed as 3 terms. The first one is the expectation of the log prior of each individual weight and the entropy of each Q of Wi. Right? So the first term and the third term are both analytical, tractable. That means they have closed form. You don't need to worry about that. The trouble comes from the middle term. So the middle term is a summation over each data point, where each summand is the expectation of the log likelihood. And the expectation is taken under the original posterior of the neural network weights. Right? So unfortunately, this expected log likelihood doesn't have any closed form. Why? Yes, exactly, right? When we look at how we compute the prediction of the neural network, right? So we use a very succinct note, it's FWXN, but the whole computation is very complicated, right? You're doing a series of like composite calculation. You're gonna first do the linear transformation in the first layer, and nonlinear activation, and then do the linear transformation in the second layer, nonlinear activation function. You keep doing that until you reach the last layer. You can see that this kind of recursive, nested linear, nonlinear transformations make this whole output highly complicated with respect to W. Right? So now if you take expectation of this complicated function of W under Q of W, no one is gonna tell you what's the closed form is. So that comes from a problem, right? Because our goal is to maximize the evidence lower bound to find the optimal posterior parameters, right? Those posterior parameters are inside Q, right? So one term inside this evidence lower bound doesn't have any closed form. So how can we maximize it? How can we optimize it? Any thought? That relates to what we have discussed in the last lecture, right? The stochastic optimization framework. Okay? Remember, the stochastic optimization framework aims to maximize a function that can be written as a form of expectation, right? So this is a general form of. Yes, exactly. That's something we're going to discuss in a minute. Yeah, right. Yes. Yeah, you're right. But let us do it step by step. Like we're going to first talk about why we cannot directly use it, and then how can we sidestep this issue. Okay. But let's first quickly review the stochastic optimization framework. Right? In general, stochastic optimization aims to optimize a function in the form of expectation of some random function, right? So this random function contains both the target parameters we want to optimize and some random variable u. And outside, you're going to take expectation under some distribution of u. Right? And in many cases, if this random function is complicated, you take its expectation outside, you even do not have any closed form. So stochastic optimization leverages an idea that, okay, if I want to compute the gradient of the expectation of this guy, right? In many cases, like if your upper bound, lower bound of integral has nothing to do with theta, and if this f is continuous, you actually can switch expectation and gradient. So basically, in most cases in practice, it can be written as expectation of gradient. Right? So this observation is very, very important because it tells us a way to approximate the gradient. Right? That is, we can first sample a u, right? Sample a u from P of u, and then we substitute u tilde to u, right? Then calculate the gradient of this random function where u is instantiated with u tilde. Right? So this is called a stochastic estimate of the gradient. Why? Because if we take expectation with respect to u, we can recover the exact gradient. Right? That's why we call it unbiased estimate of the gradient or stochastic gradient. And there is a beautiful and powerful theorem which can show that if we can just update the model parameters with stochastic gradient, and if our step size satisfies some conditions which we have discussed in our previous lecture, it guarantees to converge to some local minimum of your objective function. Right? So, and more precisely, it should be described as with probability 1 or almost surely, which I don't want to discuss what's the exact meaning of that. But basically, as long as you can represent your objective as an expectation of something, you can always calculate the stochastic estimate of that gradient. Because every time you can sample some instance from this distribution under which you take expectation and then substitute it into this function and calculate gradient as the stochastic estimate or unbiased estimate. So it seems that we have here in the directional inference for Bayesian neural network, we have met such kind of situation, right? And this is an expectation of log likelihood, right? And we don't know the exact form of the expectation, but we do need to take the gradient of the neural network parameter of this expected log likelihood. So why not we just apply the idea of stochastic optimization, right? Which is a simple instance of W and substitute it into this log likelihood and just take gradient of this log likelihood. Right? Does it work? Someone has pointed out it doesn't work. Right? So let's see what will happen. Right? So we know that in the variational inference for Bayesian neural network, the key question is how to compute the stochastic gradient or unbiased estimate of the gradient of each expected log likelihood, and the expectation is under the variational approximation of the posterior, right? Q of W. So if we just naively apply the idea we introduced in stochastic optimization, that means, okay, we can use current parameters to sample W. That means we got W hat sampled from Q of W given your variational parameters, right? Now you just substitute this W hat to this log likelihood and compute the gradient of this log likelihood with respect to W, right? With respect to the variational parameters theta, right? And this is totally wrong. And if you do this, this will simply give you 0. Why?
Nothing random.
Yes.
Fix the parameter.
Yes. Yes. Remember, when we compute the log likelihood here, this log likelihood actually doesn't involve any posterior mean and variance for W, right? Once you sample a particular example of W, like you might have W equals to 0.1, 0.2, 0.3, blah, 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 right? You just use those weights to compute the output. The whole computation doesn't involve the variational parameters at all, right? Where is the posterior mean of W? Where is the posterior variance of W? They are not directly involved into the log likelihood. That means if you instantiate W, right, you can calculate that, but this whole log likelihood, which W is fixed, where W is fixed, it's just constant to W to the variational posterior mean and variational posterior variance. If you take gradient with respect to them, you simply give 0. So now I want to ask, what's the problem, right? At which step we make a wrong? We make a wrong thing, right? Where is the step there must be something wrong here, right? Otherwise it's not possible to get absurd result, right? In which step we're doing wrong?
From outside the expectation to inside the expectation, but the expectation itself has a parameter. It's over the solution that contains the parameter.
Yes.
You are not allowed to.
Yes. Yes, you're right. Any other who wants to supplement his point? Yeah, he's the point, but I want to listen to other suggestions as well. Mm-hmm. Yes, yes, yeah. So let me summarize. I'll merge the comments from you two together. Right? So basically, when you do a sample, let us go back. Right? We will generate a sample from this posterior approximate distribution. Right? Your sample actually implicitly depends on the variational parameters, right? But then when you fit this sample into this log likelihood, when you compute the gradient only with respect to mu and theta, you actually ignore this dependency. And unfortunately, your log likelihood does not directly depends on mu and theta. Right? The dependency actually comes from here. Right? You got it depends on W hat, then W hat depends on theta. Right? It doesn't directly depend on theta. If you just calculate the gradient directly with respect to theta, it just gives you 0. Right? So if you want to get a correct result, you must account for the dependency between this random sample W hat and theta. That explains why when your distribution on which you take expectation contains parameters, you cannot simply switch the expectation and gradient. Okay. So I think if we write down the whole definition, it will be even more clear. Right? So this guy is this expected log likelihood, right? So if you take a gradient of this integral, it is okay that you move this gradient inside integral. However, you cannot move the gradient only toward the log likelihood, because another term in the integral, which is the directional posterior, is also related to theta, right? So a more precise or accurate gradient should be something like that. You should take the gradient of this product, right? You cannot view this Q of W given theta as a constant theta, right? That's why if you just move in here, right, as we just did before, it's wrong. And mathematically, if you're just doing this and you just take the gradient, and you can address that problem. But there's some issue with that, right? So because this guy is kind of constant to theta, right? So that means you're gonna take the gradient of this posterior density times logarithm log likelihood E of W, right? Once you take this gradient, well, it's hard to say if this guy will still correspond to some expectation of something, right? If you cannot reduce it to an expectation of something, it's very hard to apply the stochastic optimization idea. Remember, stochastic optimization idea is always ask us to rearrange our objective in the form of some expectation, right? And now you take the gradient of the probability density, right? The gradient probability density not necessarily correspond to another probability density. So it's not guaranteed that you're gonna rearrange this form into another expectation. And then how do you apply stochastic optimization again? So to address this problem, log likelihood doesn't include variational parameters, right? So to address this problem, here comes the very important trick. It's called Re-Parameterization Trick, right? So what's the Re-Parameterization Trick? The idea is simply to get rid of these unknown parameters in the distribution. So I want to convert this expectation into another expectation, or this expectation, under this expectation, the distribution has nothing to do with the parameter theta. In our case, it will be the variational posterior mean and variance. And in this case, because the distribution on which you take expectation has nothing to do with parameters, then if you take the gradient, you can safely switch the expectation and the gradient operation. Does it make sense? And the question is, how can we convert it? Actually, in many distribution, continuous distribution, we have some kind of like uncentralized representation, and actually everybody is familiar with that. So if we take a look at the definition of Q of W, we know it is a fully factorized Gaussian, right? So that means for any weight element like Wi, because it follows Gaussian, right? So we know that it can be represented by a linear transformation of a standard Gaussian random variable. Right? Sometimes people call it Gaussian noise, or whatever. A Gaussian distributed random variable can always be represented as a linear transformation of a standard Gaussian distribution, a distributed random variable. Right? So here we denote it by epsilon I. Epsilon I is sampled from the standard Gaussian distribution. So Wi can be represented by mu of I, the mean here, plus the standard deviation of this Gaussian distribution times epsilon I, right? Right, I believe everyone knows that, right? So you can always compute a linear transformation of Gaussian random variable is also always Gaussian random variable, and the mean will be this guy, and covariance will be square of this guy, right? Which exactly cover the distribution of W. So now we can see that we can pre-sample a bunch of standard Gaussian random variables, epsilon 1, epsilon 2 to epsilon whatever, right? And then we can re-parameterize each neural network parameters by the linear transformation of those standard Gaussian random variables, or standard Gaussian noise. In this way, we re-parameterize our neural network parameter as a function of the parameter we want to optimize, theta, which includes mu i's and rho i's and some standard Gaussian noise. Right? What's the benefit of that? The benefit is that now our W, the neural network weights, can be represented as a function of a standard Gaussian distribution. Right? If we take a look at our log likelihood, right? The log likelihood is a function of W, right? And W is a function of the standard Gaussian noise. That means the log likelihood is also a function of standard Gaussian noise. So your expectation can now be represented as taken under standard Gaussian distribution. And standard Gaussian distribution have nothing to do with the parameters theta we want to optimize. Does it make sense? Any question? This is kind of a very simple idea, but it's a brilliant idea, right? So basically, now you change your integral under a parameterized distribution to the integral under a standard form of distribution. And standard form of distribution doesn't contain any parameters we want to optimize. Then, if you take the gradient on this integral, if we take a look at here, right, it is equivalent to take a gradient, which doing integration of the standard Gaussian density multiplied is log likelihood. And now you can switch integral and the gradient, because this guy is constant to theta. You can move P of theta outside. Now you only need to take the gradient of the log likelihood with respect to theta. And this essentially is the expectation of the log likelihood under standard Gaussian distribution. Does it make sense? Any questions so far? Is everyone comfortable with this? Okay. So here we list the kind of like more detailed derivation. It's very simple, but I mean, if you feel a little bit uncomfortable seeing these lengthy symbols, you can just spend a few more minutes after class to look at this. Really just applying the definition things. So we can immediately get that the gradient of the expected log likelihood under the variational posterior now is the expectation of the gradient of log likelihood when you re-parameterize your neural network weights according to the standard Gaussian noise. And because the expectation is under the standard Gaussian distribution, so you can safely sample a particular epsilon and substitute into that and calculate the gradient accordingly, that will be a unbiased stochastic estimate of gradient. You can safely use that for any stochastic optimization algorithm. So this is called stochastic gradient ascent. Yeah, this is ascent because we're maximizing the model evidence level. Yes. No. Yeah. Not only apply for Gaussian. There are a bunch of methods, a bunch of distributions. They have the Re-Parameterization trick, but there are others which they don't have, like Mr. Gaussian. They don't have it. Like if you parameterize both weights and the components, like mu j and sigma j, and if you want to do a re-parameterize on that, it's very hard. So people have a this is kind of like frontier research. If you want to introduce a more complicated posterior approximation form, how can you develop a convenient re-parameterization? And another example I can tell is the categorical distribution. Like because in many real world applications, people are more interested in classification. Like suppose I want to classify 10 objects or 100 objects. And then we know that the distribution essentially is a discrete distribution, right? It's a softmax distribution. The problem is that, okay, can I use re-parameterization trick to optimize the parameters? The answer is no. And how do you do that? Right, so there's a very recent work. It's called Gabel or concrete distribution. They put some like a continuous relaxation of the categorical distribution. So basically, the categorical distribution is a continuous value. It's not a discrete value. And in that sense, you can come out some kind of like trick, re-parameterization trick. You sample some uniform distribution parameters and throw some logarithm transformation, some kind of other kind of transformation. You can guarantee that after that transformation, it follows this Gabel or concrete distribution. So actually, it's quite a nice research direction. But because in most of the cases, people are used to using Gaussian distribution because it's so convenient. And Gaussian distribution has such a nice property that there's a linear representation, a linear transformation. And so this I'd say that this is still the most common used case for the Gaussian distribution. But for others, there is, but not guaranteed to cover all possible distributions. Any other question? Mm-hmm. Mm-hmm. You can use categorical likelihood, but it's not. It's like if you assume your latent random variables are categorical, the parameters are categorical. How do you optimize it? Yeah. This is for this because your Q of W here you still assume it's Gaussian, right? Yeah, but what if you assume Q of W is categorical distribution? Yeah, there is some case in the for that need. It's not always like you want to estimate a continuous estimate posterior distribution for a continuous variable. There is some need like you want to estimate posterior distribution for a discrete variable. In that sense, well, they would like to also introduce some re-parameterization trick. Otherwise, you still have to face this integral expectation problem. Yeah. Everyone feels comfortable? Okay, perfect. This is a very simple, yet very important trick. I almost like all the modern neural network training, they're kind of evolving such kind of like re-parameterization trick. And then, if you look at the general case where we consider both a very large scale training data set and also the need to estimate posterior distribution of the model parameters, and then we can combine this mini batch strategy and also the re-parameterization trick together, right? So imagine you're gonna partition or random partition the whole training set into many small mini batches, and we will like there's kind of like a mini batch selector or indicator, right? You're gonna first sample which particular mini batch you want to compute, and then inside mini batch you're gonna compute the expected log likelihood. So last lecture we have mentioned that if your loss function or your evidence lower bound can be written as additive across the whole training set, you can always written as a partitioned way. Right? You can partition them into many batches, and then inside each partition you multiply a factor, that is the total size of training set, divided by the size of mini batch. But outside you have B or N. Doing this is simply to create a representation of the additional discrete random variables, right? Which is U here, and the U can be 1, 2, 3, 4, can be index of this mini batches, and this B of N just means B over N just means the probability that U takes an arbitrary mini batch. And then doing this, a slight transformation of the objective function, we can will this as an expectation under these mini batch indicators or selectors. And then inside each mini batch, by leveraging the re-parameterization trick, we can will as expectation under some standard Gaussian distribution, and then take a logarithm of the log likelihood where the neural network parameters is represented by the transformation of the variational parameters and this standard Gaussian noise epsilon. And then imagine that our training is to sample a mini batch and sample a epsilon, and then you just compute the gradient of this. And then this gives you a stochastic gradient with which you can update parameters. Does it make sense? So now we can take a look at the algorithm framework. Right? So here's how we run this by backpropagation. So first, we can initialize our variational parameters for the approximate posterior randomly. And then we just go through many iterations, right? Inside each iteration, first we're gonna sample a mini batch from P of U. U here is mini batch index, right? And then we sample an instance from the standard Gaussian distribution, or in other words, we sample standard Gaussian noise. Then, according to the mini batch index and also the Gaussian noise, we compute the stochastic gradient, right? So here, alpha theta is just those terms which can be derived in a closed form, right? Which is just this form we mentioned. Those terms we mentioned that they are all, the analytical form, and then the K is here, right? Inside each mini batch, you just substitute epsilon into that, and then just calculate the gradient, and this is guaranteed to be unbiased stochastic gradient, meaning that if you take expectation under P of U and P of epsilon, it will give you exact gradient. Then we update our variational parameters by using this stochastic gradient. Of course, we have to follow some scheduling of the step sizes, as we mentioned. Their summation must be unbounded, but square summation must be bounded, right? And then we move to the next iteration. Again, we sample a mini batch and sample the Gaussian noise and calculate the stochastic gradient, update accordingly, and so on until the maximum number of updates have finished or some other stopping criteria are met. And finally, you can give your approximate posterior distribution of the step. Okay, any questions so far? Is when everyone feels comfortable? It seems straightforward, right? So in our last homework, there's a one question asking you to implement the base backpropagation. Follow exactly this framework. Right? But again, the computation of gradient, I want to emphasize again, don't try to compute gradient by yourself. Using any automatic differentiation library like PyTorch, highly recommend. Someone would like to use JAX or TensorFlow, it's up to you. But we do not recommend you to implement the gradient computation by yourself. It's really tedious and unnecessary. Okay. And here we just mention a little bit where the backpropagation computation comes from, right? Because when we compute the log likelihood, we need to compute the prediction of the neural network, right? And the parameters of neural network, those weights, have been computed by this transformation, right? So once those weights are computed, and you can compute output and then compute log likelihood, and then when you compute the gradient with respect to theta, you have to backpropagate the gradient, right? Remember the rough procedure we have discussed before, and then apply the chain rule to get a gradient of theta. Okay? So that's where the backpropagation happens. So it's still like kind of standard to neural network itself. But again, the backpropagation and the gradient computation part has already been fulfilled by the modern automatic differentiation libraries. You, in most cases, you never need to worry about that. So once we have the predictive distribution, we can, once we have the posterior distribution of the model parameters, then we can think about how to compute the predictive distribution. And according to our definition, the predictive distribution is just an integral of the posterior distribution of model parameters, W, and then given HW, the distribution of the Y star. Okay. So now, because we want to marginalize out all the effect of the different choices of parameters, like according to the posterior, we need to calculate this integral, right? And the problem is that even we know Q of W given theta is a diagonal Gaussian, we're still not able to compute this integral. Why? Right, previously we even don't know this form, right? But now we have a simplified form Q of W given theta, which is diagonal Gaussian. But we're still not be able to compute this whole integral, namely the predicted distribution. Why? Yes, exactly right. Remember, this probability of Y or likelihood itself needs the prediction made by the neural network, right? And the prediction made by the neural network essentially is very complicated, right? You have to evolve this W and X star in a very nonlinear way, right? It's a nested and recursive computation procedure. You need first to do the linear transformation with the first layer's weights and nonlinear activation analyzed, and then linear transformation with the second layer's weights, and then nonlinear activation, keep doing until you reach the output layer, right? So even
you integrate this guy with the Gaussian, a very friendly form, you're still not able to compute the input. And then how can we approximate this predictive distribution? Now we're going to choose the same strategy as we do for Markov chain Monte sampling. Right? So we know this form, right? And then we can, using this approximate posterior, to draw a bunch of samples. And then we just enrich the likelihood evaluated under each particular sample. This is unbiased estimate of this guy. Okay. Any question so far? Everyone comfortable? Okay. So now we just want to just copy the results from the paper based by backpropagation. We have put the link in our lecture website, and if you're interested, you can take a look at the original paper. So they have compared a bunch of non-Bayesian method and some dropout method, and on this MNIST benchmark data set. MNIST is just a image classification task. It just contains digits, digital 1, 0, 1 to 9 digits. And so they show that the different methods with just point estimation, stochastic gradient descent, they can get the best performance around like 1.2% test error. And then if they use Bayes backpropagation with Gaussian prior, standard Gaussian prior over each weight, or with skew mixture prior, remember we introduced the two prior distribution over the neural network weights before, right? One is standard Gaussian, the other is just mixture of Gaussian. So it turns out that the best performance can be as good as around 1.32% of test error, which is quite close to the best result obtained by the SGD, stochastic gradient descent. So it's pretty nice. And the benefit is that we can give some uncertainty quantification. Right? In many applications, this is important. And it also shows some learning curve on that. And it turns out that if you just apply a vanilla SGD, it kind of converges faster, but just saturate too early. But if you use Bayes backpropagation, which is this blue curve, the green curve, you can see that it can go down even further. Okay? And of course, if you apply other trick like dropout, it can help. It can prevent early saturation as well. So that's why dropout is so popular in the practice of neural network training as well. By the way, there's one paper and one influential paper published a few years ago. They justify that dropout is another way of doing Bayesian inference or variational inference, and that's a very interesting paper. So it seems to tell us that doing Bayesian can save your life. Okay. So now we come to the summary of the Bayes backpropagation. So it's kind of like state of art. Neural network inference is very popular. I wouldn't say it's a state of art. I would say it's the most popular approach. Very simple, very easy to implement, and it has the same scalability to stochastic gradient descent, but it can estimate posteriors. Right? And the core idea is to apply the variational inference plus the Re-Parameterization trick. Okay? And this is also the Re-Parameterization trick is also the foundation of nearly all the modern Bayesian neural network training. So I highly recommend everybody to understand this Re-Parameterization trick. I believe this is very simple, and I try to implement it because in the future, if you want to train your neural network, you might not use some Gaussian distribution of not some Bayesian neural network, but Re-Parameterization trick is used every day. Okay, any questions so far? So the remaining part for the Bayesian neural network, we would like to introduce two classical type of neural networks, which are both have like very important, interesting probabilistic formulation. Like one is called autoencoding variational base. The other is called generative adversarial networks, and that is abbreviated as GANs. I believe most of you have heard it before, right? So we start with the variational autoencoder. Right? So what is autoencoder? Autoencoder is just a neural network implementation of the tool to do the dimension reduction. So what is dimension reduction? So basically, in real world, many kind of data are kind of high dimensional. For example, an image. Right? If I have a high resolution image, you know that it will be a dense grid. Right? If you just flatten this image, it will be a very high dimensional vector of pixels and RGB values. And in many scenarios, we don't want to store such a high dimensional things. Right? We know that between pixels are very strong correlations. If you just store them all together, it's kind of like waste of your storage. So natural motivation would be, okay, what if we can compress this high dimensional data into a much lower dimensional without losing too much information? So it's like image compression or video compression, all kinds of stuff. Right? So there are a lot of ways of doing that. If you're from ECE, you might be familiar with all kind of compression standard for images, for videos, for audios, right? But if you want to put it in a machine learning scenario, this is called dimension reduction. And for neural network people, how do they fulfill dimension reduction technique? They very commonly used technique is called autoencoder. So what does autoencoder mean? Autoencoder consists of two networks. One is called encoder network. One is called decoder network. So we can imagine that this is our original input, which is the an image, right? High dimensional image. And through encoder, we're going to compress this image into a very low dimensional representation or low dimensional vector, right? And then through this decoder, I can recover this compressed representation into the original high dimensional space. And we expect that recovered or reconstruct thing will be almost the same as the original input. That's the idea. That's called autoencoder. So I would say like autoencoder is not only important to reduce the storage, right, to save your storage, but also it's very important to denoise. For example, if you have a very noisy pixels, when you do the compression, we expect that those noises will be filtered out through this encoder. And then when you do the decoder, your recovered image will be much more clear. That's another expectation or our hope to using autoencoder to model the data and learn those low dimensional representations. So how to train a autoencoder? So suppose you have collected a bunch of data, samples, right? Maybe just a collection of images, high resolution images. Right? How do we learn the parameters for the decoder network and the encoder networks? So the loss is very interesting. The loss is like, okay, for each particular image, right, I'm going to look at first through the encoder network, I compress that image into some low dimensional vector, which we call code. And then through my decoder network, I recover or reconstruct this image through my code. I want to minimize the difference between the original image and my reconstructed image through this encoder and decoder procedure. This is very reasonable, right? I want to say, okay, well, if my autoencoder is good, then I want to see that, okay, if you put my image into my autoencoder box, right, I do some compression and do some reconstruction, I can give you almost the same thing. Right? So you're trying to minimize this loss to find the optimal parameters for the encoder networks parameters and the decoder network parameters. That's the traditional, how the traditional autoencoder is trained. So now let us switch to variational autoencoder because we're doing probabilistic things, right? Well, we want to assign some meaning, some probabilistic framework to this whole procedure, right? So what is the idea of the variational autoencoder? So in the variational autoencoder, we're gonna view or we're gonna model the decoder part as a probabilistic model. And the encoder part is actually take the role in the inference, and we'll see later. Okay. So we're going to construct a prior to sample the encoder first. To sample the code, that is low dimensional representation first. You can feel like, okay, first sample a low dimensional vector. And then through the decoder network, we sample the reconstructed image. So now we construct the probabilistic model, right? We can take a look at here. For this n training examples, for each training example, we're going to first sample is representation h of n, right? Hn. And then given hn, we sample xn through the decoder network. Right? This model is called probabilistic decoder. Okay. So now, where does this encoder kick in, right? How does encoder take the effect? Right? So for the decoder model, right, probabilistic decoder model, the commonly used prior for this latent representation is just standard Gaussian, very simple. And then, given the prediction of the decoder output, you use some distribution to sample xn. You can use Gaussian if the xn is continuous. You can use Bernoulli if your xn are kind of binary elements, whatever. Right? Later we'll discuss some details. Right? So once we have identified this model, the goal is to estimate the posterior distribution of each representation given the data. Right? That's our goal. Right? We want to estimate this guy. That is the posterior distribution of the latent representation. And for convenience, we can assume this posterior distribution of the latent representations for n examples are factorized over each example. Right? So we want to estimate the posterior distribution of each representation for the particular example xn. And again, because we know this representation is directly related to the input image, right? So we can parameterize this posterior distribution in terms of this encoder network. That's the idea. That's where the encoder takes the effect. It serves as the component in the variational approximation of posterior, rather than just being the modeling component. It serves in the inference part. And then how you construct this guy, right? A very simple approach is that, okay, I'm going to assume this is a Gaussian, right? And the mean will be the prediction of the encoder network. So I can use it FW1 as xn, right? The input with the xn. And then you have some variance. Or you have some diagonal variance, whatever you want. So you can see that in this way, the mean of this variational posterior is modeled by the encoder network, right? And it's very natural because, different images, latent representations should be determined by the image itself, right? So it should, through some kind of nonlinear transformation and compression procedure to get to the mean of this representation, right? And here we just assume this transformation can be represented by an encoder network. Any questions so far? Okay. So we use neural network output to parameterize the variational parameter, namely the encoder, right? And then we can just shove our model, and the variational posterior, our model is parameterized and is determined by the decoder, and our approximate posterior is determined by the encoder. Now we can construct a variational model evidence lower bound, right? And it has this form, right? So this is the encoder, probabilistic encoder, which tells us how do we parameterize our variational posterior of the representation of each image. And this is the joint probability, where you sample the representation from some standard Gaussian and then reconstruct the image through some decoder network's output, right? And divided by the probabilistic encoder, and then that's it. And of course, both the joint probability and the variational posterior involves the computation of neural network output, right? So it's, of course, it never gives you an analytical form. How can we optimize it? How can we maximize this lower bound? The re-parameterization trick, right? We can just use the re-parameterization trick we just discussed. And then plus the cost optimization on many batches. Any questions so far? Yeah, I believe everybody has captured the idea, right? And this paper, I mean, is very, very simple. It was published maybe 9 years ago. Yeah, 9 years ago. And everyone who knows variational inference feel like it's so easy, right? So directly, but it is, I guess, the top 3 highly cited work in the neural network world. If you can take a look, I guess it's the citation is more than 30K or something like that. It's very hard. But the idea is really, really simple. It's just they also come out way to combine the decoder and the encoder, but they just place them into the construction of variational evidence lower bound. That's it. And now, I think in the remaining a few minutes, I just want to give you a concrete case to show how this attached to the practical example. For example, if this is your image, right? This is your image, and if you want to construct your decoder network, meaning that given HM, you want to predict the whole image or reconstruct whole image. Right? Of course, this is a probabilistic encoder. That means we have a mean, we have variance. And a commonly used approach is that, okay, we're going to use neural network, the decoder network, to predict both the mean and the variance, rather than assuming a constant variance. Why? This is reasonable because each pixel, when it varies, the locations, it might have different variances as well, right? So to achieve like maximal flexibility, we might want to join to the model at each location. What is the mean? What is the variance? So a common user strategy that, okay, my decoder network will have 2 outputs. One output is the mean, and the other output is the variance. Of course, we need to do some kind of like a transformation to ensure this variance is positive. That's how people are defining the probabilistic decoder, namely given Hn, how we sample Xn. And for the, if your image is not like continuous value, like continuous RGB values, instead it's binary values. You can see that your image is 0, 1s, right? But even with 0, 1s, you can see the shape of this horse, right? And then if that is much simpler, you can just generate one output and then parameterize this output as a probability, and then you can construct the Bernoulli distribution. Okay. Any question? Okay. And this is for this is the example to construct the decoder network. It really depends on the data type of the type of the data. Right? But for the encoder, because encoder is in a latent space, in a low dimensional space, it's really more comfortable for people to assume it is a continuous variables. So that's why no matter what kind of actual type of the data we have in the latent space, we always assume this H, the latent representation, is a continuous. So we're going to model the variational posterior, namely the encoder, as a Gaussian distribution. And now that it's Gaussian distribution, it must have mean and variance. And we model both mean and variance with the encoder network. That means we usually use a network has two outputs. One output generates the mean, the other output generates the variance. Then we can use these two networks to construct your variational evidence lower bound and use Re-Parameterization Trick, Stochastic Optimization to implement the learning of those problems. So summary of the variational autoencoder. It's a nice work that converts the classical autoencoder estimation into a probabilistic inference problem. It endows you the capability of estimating variances and uncertainty, right? And but it's a trivial application of variational inference. It's a kind of state of art right now. When you're doing compression, people always use variational autoencoder rather than standard autoencoder, and it's quite hot. Maybe it's not very hot right now, but it's quite hot. Okay, yeah, let's stop here today, and see you on Thursday.
Hi. Is session.
What?
The next
This Thursday.
Is the last session?
No, the last lecture, the end of lecture will be next Tuesday. Yeah, we still have 2 lectures. Yeah.